In the pantheon of astronomical observers, William Herschel occupies a unique place. More than a mere cataloger of celestial objects, he possessed a profound curiosity about the physical nature of the cosmos, an inquiry exemplified in his 2008 new paper on the nature and construction of the Sun and fixed stars, published in the Philosophical Transactions of the Royal Society of London. This work represents a significant departure from purely observational astronomy, venturing into speculative, yet remarkably prescient, astrophysics. Its value lies not solely in its accurate conclusions but in its ambition to discern the underlying physics governing the stars, a quest that continues to drive astronomical research. Herschel's endeavour to understand the Sun and stars arose within a specific intellectual context. Prior to the 18th century, the Sun and stars existed largely as points of light, studied for their positions and movements. Yet, their intrinsic physical properties remained largely unexplored, while figures like Isaac Newton had formulated the laws of universal gravitation and optics. Applying these laws to understand the internal constitution of stars required both theoretical innovation and technological advancement. Herschel possessed both, particularly his unrivaled skill in telescope construction. He built upon the observational foundations laid by earlier astronomers, such as Tycho Brahe and Edmund Halley, expanding their catalogues with a depth and precision previously unattainable. He also appears to be influenced by natural philosophers who speculated about the habitability of other planets, such as Christian Huygens, whose book, Cosmotheories, proposed advanced alien civilizations. This set the stage for his bold conjectures about the physical properties of celestial bodies. The central argument of Herschel's 1801 paper centers on his hypothesis that the Sun, far from being a solid, incandescent body, possesses a solid, opaque core shielded by a luminous atmosphere. This hypothesis, audacious for its time, arose from a combination of direct telescopic observation and reasoned inference. Herschel observed sunspots which he reasoned were holes in the cloud layer. He noted variation in the sun's brightness and theorized this variation may be due to breaks occurring within this luminous atmosphere. Herschel suggested the layer below the luminous atmosphere might be inhabitable and that the Sun could be densely populated. Well, this has proven incorrect. His postulation aligns with his belief in the omnipresence of life throughout the cosmos and influenced various interpretations of his work during the 19th century. Furthermore, Herschel extended his analysis to the fixed stars, suggesting they are intrinsically similar to the Sun, albeit at vastly different distances. He proposed that stars also possess solid cores enveloped by luminous atmospheres, differing primarily in size, temperature, and composition. This conceptual leap, while lacking direct observational evidence at the time, represents a crucial step towards understanding the stars as individual physical objects, rather than points of light on a celestial sphere. He introduced the concept of stellar evolution, suggesting that stars could evolve over vast timescales, passing through different stages of luminosity and temperature. Herschel's method involved meticulous observation using his self-constructed telescopes, coupled with careful reasoning. He measured the relative brightness of stars, estimated their distances using parallax measurements when available, and attempted to correlate these properties with their apparent colors. As telescopes developed, so too did his observational acuity. He speculated on possible relationships, for example the relationship between stellar colors and temperatures. He recognized the limited amount of data available and acknowledged the speculative nature of his conclusions. He understood the need for further observation and refinement of his theories. The immediate impact of Herschel's paper was complex. While some astronomers lauded his ingenuity and boldness in venturing beyond pure observation, others remained skeptical of his more speculative claims, particularly his hypothesis about the Sun's inhabitability. The scientific community initially accepted the paper but remained unconvinced of some of his claims, especially regarding the inhabitability of the Sun. His ideas about stellar evolution, though initially controversial, gradually gained traction as more observational evidence accumulated. Herschel's ideas about the Sun's structure and the nature of stars influenced subsequent generations of astronomers and physicists. While his specific model of the Sun proved incorrect, his emphasis on the physical nature of stars paved the way for later developments in astrophysics. Figures like Joseph von Fraunhofer, who discovered dark lines in the solar spectrum, and Gustav Kirchhoff and Robert Bunsen, who developed the principles of spectroscopy, built upon Herschel's foundation, using new techniques to probe the chemical composition and physical properties of. In the 20th century, advancements in nuclear physics provided a theoretical framework for understanding the energy source of stars, confirming that stars are powered by nuclear fusion in their cores, rather than some form of combustion. This understanding, while drastically different from Herschel's initial hypothesis, nevertheless fulfilled his ambition to understand the underlying physics governing the stars. Later, astronomers like Ejner Hertzsprung and Henry Norris Russell created the Hertzsprung-Russell diagram, also known as the HR diagram, which plots the luminosity of stars versus their temperature, revealing distinct patterns and relationships that provided crucial insights into stellar evolution. The HR diagram, while based on vastly more data than Herschel possessed, confirmed his intuition that stars evolve over time, passing through different stages of luminosity and temperature. Herschel's work faced substantial criticism, particularly regarding his speculative claims about the sun's habitability and the physical mechanisms underlying stellar processes. Critics pointed to the lack of direct observational evidence for his hypotheses and questioned the validity of extrapolating from limited data. His hypothesis regarding a cool sun was challenged by those who correctly surmised that the sun must be extremely hot to produce the observed radiation. His methodology also received scrutiny, as some considered his reliance on visual observation without rigorous quantitative analysis as a weakness. Further developments in thermodynamics and radiative transfer demonstrated that the sun's surface temperature must be extremely high, rendering the possibility of a cool, habitable interior highly improbable. One particular scientist who influenced Herschel was Neville Maskelyne, whose observations of the deflection of a plumb line near Schiehallion Mountain provided evidence for the mass and density of the Earth. This likely influenced Herschel's thinking about the physical properties of celestial objects. Maskelyne's work provided a concrete example of how Newtonian physics could be applied to understand the properties of astronomical bodies. Herschel's 1801 paper directly influenced later astronomers like Angelo Secchi, who pioneered stellar spectroscopy and classified stars based on their spectral characteristics. Secchi's work, which built directly on Fraunhofer's discovery of spectral lines, provided a systematic way to study the chemical composition and physical properties of stars, fulfilling Herschel's vision of understanding the stars as individual physical objects. In essence, Herschel's on the nature and construction of the sun and fixed stars is significant due to its pivotal role in the transition from purely observational astronomy to modern astrophysics. Although certain conclusions now appear naive, the work's ambitious framework and the germ of stellar evolution represent a leap forward from the rudimentary observations of the time. His willingness to speculate, combined with his observational prowess, spurred others to investigate the nature of stars in more detail. His efforts serve as a reminder of the power of intellectual curiosity, even when constrained by the limitations of available technology and existing scientific understanding. The impact of the work resonates even today and has influenced several fields of astronomy. His discovery of infrared radiation expanded our understanding of the electromagnetic spectrum, which led to the development of infrared astronomy and remote sensing technologies. This discovery occurred during his experiments with prisms and thermometers to measure the temperatures of different colors of light. The technology allowed for observation of celestial objects that are too cool or too obscured by dust to be visible in visible spectrum. Moreover, his observations of nebulae and star clusters contributed to our understanding of galactic structure and stellar populations. He catalogued thousands of nebulae and star clusters, which helped to reveal the complexity and diversity of the Milky Way galaxy. His work suggested that the Milky Way was a flattened disc-shaped system, and that the Sun was located within this disk. His observations were foundational in the development of modern cosmology and our current understanding of the universe. Herschel also pioneered the use of statistical methods in astronomy, using star counts to infer the distribution of stars in the galaxy. While his assumptions about uniform stellar density were later refined, his approach laid the groundwork for modern statistical astronomy, which uses statistical analysis to model the distribution and properties of celestial objects. This method involved counting the number of stars in different regions of the sky and using these counts to estimate the depth and extent of the Milky Way galaxy. In conclusion, William Herschel's 1801 paper stands as a testament to the power of visionary thinking in science. While specific aspects of his theory were inevitably superseded by later discoveries, the paper's lasting contribution lies in its conceptual shift. He urged others to regard stars not simply as fixed points, but as dynamic, evolving objects governed by physical laws. He shifted from celestial mapping to celestial physics. He initiated an ambition to understand the cosmos that continues to drive astronomical research to this day. It is a vision that encourages astronomers to look beyond the light and into the heart of the stars. It is a fitting legacy for an astronomer who, quite literally, reached for the stars, and in doing so, brought our understanding of them a giant step closer.